So today I am going to be talking about the past, present, and possible future of nuclear energy, particularly in Michigan. Palisades Nuclear Power Plant is why I am here for the most part, but I will say today in the presentation, I'm going to speak very little about Palisades in particular. You all see the news stories, you all see the day-to-day of working at a power plant or working with, or knowing people who have worked here. So I'm going to try to give the overarching content around the nuclear industry and the history of it and the possible future of it, so that as you are all reading those news stories, you can contextualize it in that way. I would also say the inner workings of this particular power plant are not the topic of my thesis. The topic of my work has been about how power plants like this operate within the larger energy system. And that is something that we all need to think about. And by energy system, I don't just mean the electrons flowing through wires. This is about how it works with economies, it works with the communities around them, and the technologies that are operating within them. So with that in mind, I will today talk about the history of the nuclear power, how these power plants work, generally speaking. This will not be like a college lecture where I'm telling you about reactions and neutrons and all that fun stuff. The two topics which come up every time I say nuclear to anybody, disasters and waste. We're going to talk about why are we still interested in nuclear energy, small modular reactors as a key piece of that, and then briefly Palisades. So jumping right into it, we'll go to the 1940s, where we had our first nuclear reaction that took place, driven by human power. It was less than a watt of energy it produced. Just a few years later, they powered some light bulbs with nuclear energy. This was about a kilowatt of electricity for primarily military purposes. And then a few years past that, in 1954, the first nuclear power plant provided electricity to an energy grid. This was in the USSR, and it was all the way up to 10 megawatts. We then started powering our submarines with this. So the S1W was the first pressurized water reactor that really started being used in the processes that we think about today. This was a project piloted by Admiral Rickover. I might mention him a few times throughout the day today. And a few years later, as part of a government-driven process with Admiral Rickover at the lead, we had Shippingport Power Station that was generating electricity in the United States to the grid for electricity purposes. In 1961 was the first time a non-governmental power plant was connected to the grid. This is Yankee Row in Massachusetts. It operated for many years and eventually shut down, having lived past its expected lifetime, actually. It was all the way up to 186 megawatts. And then finally we get to 1971 when Palisades was started for the first time at 800 megawatts. This brief history here shows us two key things about the nuclear industry, which we're still dealing with today. Throughout its history, it's just gotten bigger. Nuclear power started very small, with these very small reactions as a proof of concept, and then it continued getting bigger and bigger and bigger. And that is because up until the 1970s, that made it cheaper and cheaper and cheaper. Economies of scale, the bigger you make something, generally the cheaper it gets per unit produced. The second piece of this is that since we started using pressurized water reactors, which is a certain design type, for our submarines in the 50s, that has been the dominant type of nuclear power plant. Over 80% of nuclear power plants in the US and globally use that design. It has not diverged significantly. That's not to say other places and other methods have not gone in different directions. For example, in Canada, they have the CANDU reactors. These use a different type of fuel, different type of coolant. We have the UK. They were using the Magnox reactors. You'll notice some of these names are really fun too. This used natural uranium as the fuel and gas as the coolant instead of water. Much higher temperatures are available for that. In the USSR, there was the RBMK, which was a different type of reactor using enriched uranium now, boiling water as the coolant. This will come up in a big way later when we talk about disasters. And then we have fast breeder reactors. This was another technology that's used around the world, but in much smaller scales. This will also come up later. In fact, all of these technologies that were used in very small amounts throughout the rest of the world because they weren't on the pressurized water reactor train like we were, are starting to be technologies that we're looking at again. So this history tells one key story, but it also shows us that there are other avenues we can start to go in the coming decades. This is where we get into the fun part of how does this work? So by the end of the slide, you all are going to be experts in nuclear engineering. So we start off with a reactor pressure vessel. This is where you can think of it as water surrounding a very hot nuclear core. So this is where it generates all of the heat, the water gets hot, and we circulate it through what we'll call a primary loop. So the water gets hot, it moves up, it moves over into a steam generator. So it has to get out, it has to get that heat out somehow, which we'll talk about in a second. The water cools down and goes back into the reactor pressure vessel. This containment unit, or the containment structure here, is where all of the radioactive processes happen. Nothing goes in or out of there without strict scrutiny. Or at least I've heard. I haven't actually been inside a containment unit. Most people haven't. So this is sealed. If there is an accident, almost all accidents happen just inside this and nothing leaves. There are a few key cases where something has left, which are the ones that make the news often. But these are designed to be very safe and very structurally sound. Then we get into the second step. We've generated hot water. The hot water has made steam inside that funny pasta-looking shape thing, the heat exchanger, and that is a secondary loop. It generates hot steam. Steam goes, turns a turbine, the same way that a coal power plant does, a natural gas combined cycle power plant. This is a fundamental system in the energy world that many of the systems use. That water, the steam goes down, cools off, goes back in. Closed loop. And then you've got all the other balance of system, like the consumers, and those wonderfully fancy cooling towers that aren't actually at the Palisades plant, but everyone likes to associate with nuclear. Everybody engineers now? We're all ready to go. Okay. What is nuclear power doing for our grid right now? We haven't built much nuclear in the last few decades. That being said, nuclear power provides 19% of electricity generated today in the entire country. Almost equal amounts to all other low or no carbon electricity sources combined. Additionally, why this is so important is because when we think about how much a resource is being used versus how much it can be used, so capacity factor is a term we use a lot. Essentially, how much is it being used versus its total potential? Nuclear is over 90% in its capacity factor. These power plants turn on, stay at almost full utilization as long as they can. Oftentimes they have to turn off to refuel, and that's about it. This is very valuable because when we think about the power system, it's not just about generating as much as you possibly want. We generate the exact amount that we use in any given moment. That means that something like nuclear energy is able to provide what people call baseload. It's generating a constant amount all day, every day, so that other sources can vary to meet whatever we need moment to moment. This is a fundamental way in which we organize the power system, and is also one of the reasons why nuclear power fits really nicely on our power system because we need a diversity of resources on there. There's no one resource that will be key to solving everything. It has to be a lot of these things together. And there's very little that runs like a nuclear power plant at such high capacity factors to provide that all year round. It's not perfect. It does face significant challenges. So I'm going to talk about 4 challenges in particular today. Each of these could be a few days of me just talking at you, so I apologize, I'm going to go through them very quickly. Public image, waste, cost, and licensing. All very challenging. So let's start with maybe one of the hardest ones first, the disasters. These disasters have shaped how the entire world views nuclear energy. There is no conversation that I have, sorry, I keep moving this closer and further from my mouth, and I apologize if it's annoying for the audience here. There is no conversation I have about nuclear energy which does not come back to this. So I'm going to talk about these disasters, but I want to make two things abundantly clear before I start. The first is that these are very serious accidents, and they should by no means be minimized. The second is that these disasters are not disasters of nuclear energy, but they are disasters of policy, design, and the operation of these plants, which was not innate to nuclear energy, but to larger systemic failures. So we'll start in 1979 at 3 Mile Island. This is arguably the event that shaped the US nuclear industry over the last few decades. What happened was there was a failure in the secondary loop. So what generates the electricity? Taking heat away from the containment building. This is going to be a vast simplification. So any nuclear engineers in the room, I apologize in advance. Heat wasn't being taken away from the containment structure, the primary loop. So that water that's being used to cool the reactor started getting really hot. If you don't remove the heat, it has to go somewhere. It gets the water hotter, hotter, hotter. So it builds up a lot of pressure. The system worked correctly in releasing pressure from that system within the containment structure. It did not work correctly in closing the valve again, but the computer thought that the valve was closed. The engineers found that there was still a problem, filled it back up with water because most of the water had evaporated off, causing a partial meltdown of the core, and then a small amount of that gas got released. For the 2 million people surrounding this power plant, there was about 1 millirem of radiation exposure. To put this in context, every single year, all of us are experiencing 200 to 600 millirem by just living on this planet. If you live in a higher altitude, so I'm from Colorado, I experience about 100 millirem more depending on where I live in Colorado. These numbers are not super dangerous in terms of what they were exposed to. This was more of a policy and aftermath image issue. The systems primarily worked correctly to shut it down before there was a larger incident. Now let's talk about a larger incident. In 1986, Chernobyl. I mentioned the RBMK before. This is a boiling water reactor, but it had a problem. And the biggest problem was not the reactor design, but that the reactor design had a known flaw that was not communicated to the operators or most of the engineers. So they were operating under the assumption that this is a perfectly safe power plant. And they were not told about some key design flaws in the system that were known at the time. This is what was called a positive void coefficient. Essentially, water is what was used to cool the system and also to make sure the reactions didn't run away. But it was a boiling water reactor, and so it generated steam. If you get too hot, you generate more steam. If you have more steam, you have less water. If you have less water, you get more heat. More steam, more heat, more steam. Cascaded in less than 2 seconds, I believe. I might be wrong on that number. Very, very fast, the whole system went critical, and there was a massive explosion from a known design flaw. 30 to 45 direct deaths were associated with this, 5,000 or more cases of cancer, an area that is still under significant observation, we'll say. There are areas that you shouldn't go to in there. I would also say these numbers, I wouldn't trust them as much because of the opacity of the policy at the time. And then most recently, I heard Japan whispered somewhere out there. Yes, Fukushima Daiichi was the most recent example of a large-scale incident. In 2011, there was a series of earthquakes and then a tsunami following. All of the power plants in the area shut down correctly. What they didn't do was 10 years before, when they found out that there was a chance of this size of tsunami, they didn't increase the wall size around the power plant. And they kept the generators and backup batteries below sea level. Yeah, I heard some groans, I agree. So what happened was the tsunami wave flooded the backup generators and the batteries. Cooling systems failed. You build up the pressure, can't get the heat away fast enough. Eventually, gases with more pressure there, as well as hydrogen due to some internal reactions, built up. There was an explosion. There is up to 1 direct death associated with this, and there are more from the evacuation process. These numbers, again, are very challenging because this was a national scale disaster, not because of the power plant, but because of the earthquake and tsunami. So it's really hard to understand what numbers are from what. These are all very serious accidents that are oftentimes talked about in terms of the nuclear energy. But I also want to point out that 3 Mile Island, there was operation there until just a few years ago, power plant workers on site, and they're talking about restarting it. So the risk associated with being on that site still is very low, even with how large the overarching effect was. Chernobyl, more significant. But there's still workers on site every single day. They have to go through strict procedures, but there still is working on that power plant. Until 2000, I believe, their power plant was actually active still at its other units. So these are serious accidents, but there's still potential in these areas. It's not the end of the world in these locations even, particularly 3 Mile Island. The other 2 are far more serious, and I don't want to minimize how serious that fallout was. Waste. Okay, we're getting the 2 hard ones out of the way first. These are really heavy hitters. So 2,000 tons of nuclear waste is generated every year in the United States. 90% of the energy remains in that fuel after it's used. There are 3 methods I'll talk about for dealing with waste. The first is what currently happens in the United States. The nuclear waste is safely stored in these concrete and metal casks on site. In this case, in the picture, above ground. In other cases, it's stored in retention ponds. The safety risks associated with this are fairly low, as long as someone doesn't go around trying to break into them and damage them. But they're all waiting for a permanent location. This was always a temporary thing. The permanent location was previously decided a long time ago to be Yucca Mountain in the United States. I won't get into the politics or the decision-making behind that or why it wasn't chosen, but it wasn't chosen by the folks around Yucca Mountain, I'll say that. So that was a deep geologic repository. You essentially are storing the nuclear waste deep underground. There is virtually no risk to those above ground, to the ecosystems, water systems. It is a very proven system, especially when it's already within these casks. In some cases, nations, for example, like the US with Yucca Mountain, have decided this is where it's going to go. Other nations, and what the US is hoping to do in the future, is a participatory structure. Sweden, for example, put out a bidding process to all their communities, saying, who wants to host this? Who wants the nuclear waste for our entire country? Oh, by the way, what comes with it is low risk, but jobs for 100,000 years. Probably not jobs that long. Infrastructure. You get better road systems, better electricity provision, and you get a lot of money for your community. Who wants that? And there was a bidding process. So it was a participatory structure rather than top-down. The final method I'll talk about is dealing with that 90% of energy that remains in the fuel, that remains in the waste. What if we were able to reduce that? What if we didn't have as much waste? So there are different reactor designs that are able to use this low-grade fuel. In fact, one of the reactors I'll talk about later on, which is furthest along in the process, going through licensing right now, does this exact thing. It's able to use the waste fuel of other nuclear power plants and reduce it down to 1/10 of what it was before. Pretty good deal. It seems like economically speaking, if you're using something more, if you're using a waste product, Seems pretty good. If you're reducing waste, that seems pretty good also. All of these are different methods. I'm sure that there will be different uses and different balances of this in the future. But it is still an active challenge that's being worked on. Okay, less challenging topic, cost. Nuclear costs have arguably been the biggest thing that has stopped them from continuing in the United States in particular. This power plant right here is, I would argue, a poster child of some of the challenges that have been faced. This is the Vogtle power plant in Georgia. It was 7 years over timeline and over double the budget when it was finally built. This fits a larger trend. I apologize, this is a very small figure. X-axis is how much has been built, y-axis is cost. For a long time, as we said, it was getting, so we were building bigger and bigger, and so it got cheaper and cheaper. And then it stopped getting cheaper. Once we got to a certain size, everything got much more expensive. And every single power plant built after that was more and more expensive. Part of this has to do with the fact that almost every single nuclear power plant is a unique design. And so every single site, you have to completely redesign the system. One power plant, they actually built backwards for the first few years. Don't ask me how that happened. But it also does fit something that Admiral Rickover said at the very beginning. Every nuclear power plant gets built ahead of schedule and under budget until it's built. This is one of the biggest challenges we need to deal with. And then there's licensing. I'm sure all of you have seen NRC in your news, locally or nationally, a lot recently. Licensing is a very complex topic. I'm not a licensing expert. Compared to the other things, I do a lot of techno-economic assessments. Licensing is more challenging. In this image here, we have the initial process. It was a two-part process. You get a permit to build, and you get a license to operate. 98% of nuclear power plants operating today went through this licensing process. It's called Part 50. And then very recently, in the 80s, they built a new licensing process called Part 52, where they just kind of smushed this all together. So now you just need to go through one process. Only 2% of power plants have actually used that. It's being used right now by one of the advanced reactors. Now the problem is, most of the licensing processes are very rigorous, which is great, but they're also designed for certain processes like starting up a pressurized water reactor. Remember, over 80% of our designs are pressurized water reactors. So when we start introducing new reactor designs into the mix, licensing becomes a lot more challenging. How do we both guarantee the safety, but also not say, well, this doesn't fit the pressurized water reactor design process, so we can't build this. So there's a new one that they're talking about putting into place in the next few years. Debatable, because it's going back and forth between the NRC and Congress. Back and forth. It's called Part 53. It's supposed to be designed to handle more reactor designs. I showed those other types of reactors at the bottom in our history. Many types. How do we license those? How do we guarantee they're safe, but also not overwhelm them to make sure that they can't get built? This is a big challenge. Okay, that was lots of challenges. Why are we interested in nuclear if there's all these challenges? The load within the United States is expected to grow almost fivefold over the next 5 years. I said that wrong. The load growth is fivefold growth. It's not going to be 5 times the load. This means within our market region here, so our market of MISO, which is where Michigan sits, they're expecting capacity shortfalls. You're not able to have enough capacity on the grid to serve demand at key peak times over the next few summers. So let's build more. But then we have companies like GE Vernova, which supplies a lot of the turbines for gas plants. Everyone's talking about building gas plants right now. They're seeing backlogs. You can't even start to order a new turbine before 2028. Seems kind of challenging. Siemens, same thing. These turbine companies are overwhelmed. We can't build enough of these things fast enough for what some of these companies want. At the same time, we're saying, in many cases, that we want to just build lots of gas. That's what lots of companies want to do. They want to do all natural gas. In the past, they said this with coal. But there are cases where, for example, Wisconsin ratepayers bought a coal plant. It got retired early because it wasn't economical to run. And so it became what's called a stranded asset. Every single month, consumers are paying $2.48 to pay off a plant that is no longer operating. Those same ratepayers are being asked to pay $2 billion for gas plants. How can we guarantee that there isn't a stranded asset there? I would argue this comes down to building a diverse grid. We need resources from everything. The more we have all these different resources together, the more you're going to be able to avoid some of these stranded asset costs. If everybody builds natural gas plants, what if the cost goes up? How do we weather this system? And it's through diversity of resources. And then finally, the topic you have to talk about for load growth or nuclear energy these days, artificial intelligence and data centers. Every day I see a news story, because I've got a very curated energy feed, about the load growth went up 7 times, it went down 7 times, it went up 7 times, it went down 20 times because of new algorithms. These companies, data companies, computation companies, need as much power as they can get. One of the benefits, in some ways, to this is that companies like Google, Microsoft, tend to have corporate pledges to where they get their energy. And so they don't want to say, well, we'll get it from anywhere. They're saying, well, we need constant high energy, so we're willing to pay more for early advanced nuclear energy. Invest in it now. The cost will go down in theory later on. But we get the benefit of it early on. And so they are some of the driving forces behind nuclear energy's reimagining in the last decade and in the decades to come. Also one of the largest drivers of the growth that's causing some of the challenges in the first place. It's a cycle. So that reimagining comes with a lot of different designs. We can't just rely on the same pressurized water reactor that's 1,000 megawatts that we've done for the last few decades. We need to think about how to do it differently. The first level of this that the DOE has proposed for their advanced reactor development program are these 2 reactor designs that they call the demonstration level. This is, they're getting funding, they're getting support, technical support for these reactor designs. One is the natrium reactor. This is one of those reactors that actually uses potential waste fuel from others. So it's a sodium fast reactor. Instead of water, it uses liquid sodium. So it's a very different process, but the concept remains the same. You heat up a coolant, in this case liquid lithium, generates electricity from the heat. Then you have the XE100 from X Energy. For those of you following in the news, this is the reactor design that is being applied in Texas at Dow Energy. Dow Energy, or Dow Chemical, has said, we're going to use nuclear to power our systems, and we're going to invest in X Energy. They're going to do it for us. This is a gas-cooled reactor, similar to the Magnox one in the UK, and it's high-temperature gas. It's able to produce higher temperatures. In theory, higher efficiencies come with that. So it's also the first small modular reactor that we'll see in this presentation. There's another small modular reactor that we have to think about, especially here. The SMR 300 by Holtec. This falls into the DOE's risk reduction 10 to 14 year time bracket. This is an advanced light water reactor. So imagine a miniaturized pressurized water reactor. How does that work though? How are we miniaturizing all this? And what does that actually mean for the system? So we go back to our fancy diagram, how we're generating electricity. And we replace that whole containment structure. Now we have a simplified, enclosed system that can be built in a factory and shipped on site. The primary components of it are much smaller, in theory being able to be transported. There is this rounded surface in there that is an enclosed pressure vessel. That is where the entire primary loop takes place. I don't know if it's visible throughout the entire thing, but there are no pumps anymore. Or at least there's reduced emphasis on an outside pump. Two of the three disasters that we saw before, it was a pump failure. You also are now containing it in water and a secondary containment structure. And you can get rid of lots of the extra balance of system. There still is more in there. I promise it's not this simple, but for all of our purposes today, it's reduced complexity in this manner. They are designed to be inherently safer. That is one of the key value propositions. They're more expensive, which I'll touch on in a second, but they're designed to be safer. As we said, the #1 image of nuclear energy has been shaped by disasters. This was really critical for SMR designs from the very beginning. They're designed to have passive safety measures. So that comes with simplicity. It's a contained vessel that has gravity or heat-driven coolant. If the power goes out, gravity typically still works. They also have lower amounts of fuel. So you're not going to have the same energy density to be able to run forward if you have a failure of a system into a large-scale cataclysmic event. There's multiple layers of enclosure, which are sometimes designed and built in a factory so you can test every single aspect of it before you send it to the site. You don't have to worry about on-site construction errors as part of that initial pressure vessel and enclosure system. And further, you're putting them underground and underwater mostly. So they're not only contained by a pressure vessel, but now by water, and then by a hole in the ground. So there's much more containment. One of the other aspects to these is that you're able to build them in factories mostly. That means that they're not all unique. They're not all going to be more expensive than the previous one, and you can learn by doing. Whether it's airplanes, cars, TVs, things get cheaper the more you build them, typically. That's because they don't reinvent the TV every single new TV that comes off the line. The same principle goes for why they're trying to do this with small modular reactors. Let's see. They're expensive. Again, they have not been built yet, so they're going to come in under budget. But they're very expensive even under budget. Some argue they're always going to be too expensive. There's too much risk. Can't do anything about this. Utah had an agreement with NuScale Energy, a small modular reactor company, to build these and install them in Utah. And it fell through. The costs escalated too far. So obviously that was the end of small modular reactors. We're not going to talk about them anymore, except that they're still going to be built in Dow Chemical or at Palisades. So it's obviously not the end, but we need to think about how do we actually get these onto a power system? If we can't rely on projects all working, we can't rely on the first one being built to drive the costs lower, what do we do? So now I'll do a little plug for my actual research. So this one slide is what I've done research on. We were looking at other uses for small modular reactors. They're not competitive necessarily on the electricity wholesale market. MISO, the area we're in, is a wholesale market. It's very complicated. Not a perfect wholesale market, but it's not competitive. So we looked at industrial heat. Could that be a valuable market for SMRs before electricity? These produce between 300 and 600 degrees Celsius steam. That's pretty useful, past just electricity. Depending on the context, across the entire country, 923 actual facilities that we had data for, we could deploy by 2050 1,300 modules, given different contexts. A lot of these were smaller reactor designs, like microreactors, which are a smaller version of small modular reactors. And I will say, just to make sure everyone knows, small modular reactors sounds like it's gonna fit in the back of your car. It's not. These are much larger than you'd expect from a word like small. I think some of them would probably be about the length of this room as just the reactor pressure vessel. Much smaller than a typical nuclear power plant. But I just want to make that known before we go further. Small is a bit of a funny word for it. These industrial facilities were across the entire country. There are so many different areas and so many different industrial facilities where these would be more economically viable than just running with existing natural gas for the exact same steam quality. We tested this across a bunch of different natural gas prices. The ones here in this map, and when you get up to 1,300, are $6 to $10 per MMBTU. Some of you are energy people who read the energy market news all the time and see $2 to $4. And so you might be saying, that's ridiculous. This is industrial delivered natural gas. The $2 and $4 is market price. It's at the trading level, and sometimes even at power plants, but not at industrial facilities. For example, in 2023 Michigan, the annual average was over $9 per MMBTU, which means that it was cheaper to install this new technology, small modular reactors, rather than just continue paying for natural gas. So there is an opportunity to start building these in certain markets, starting soon. It's economically viable if the costs don't increase. And that could spur the learning, the development, and the greater opportunity for them later on. I think I'm slightly over time. I apologize. What does this mean for Palisades? As I said, I'm not going to try to tell you exactly how Palisades works. I am sure some of you in the room could tell me far better how Palisades works. Well, we can start off. There's already demand. You can think about this regionally with the market that I said was seeing capacity shortfalls. It's great to add more capacity onto the grid. But there's already demand where people are trying to reserve the energy from Palisades running in the next few decades for their co-ops in Michigan. There's commercial and industrial interest. Holtec wants to build this and build their small modular reactors on the site. This is a huge step. There is market and there's opportunity here. There's also lots of challenges. This has never been done, particularly the restart of an old reactor. It's never been done. It's being discussed in multiple locations, but Michigan would be the hub of a very important change in the nuclear industry to be able to be this point where something large shifts. But there's lots of questions. Are there health impacts? People aren't sure. People haven't understood this. People are asking the questions, which are very important questions to ask. Is this power plant ready to restart? One of the reports found that of the 16,000 steam tubes, I think was the number I read, over 1,000 of them had corrosion. There's a discussion about how that's a very standard practice. You plug and you re-sleeve these steam tubes. In different reports from the NRC, they say, well, this is a new material you're using for this process. We need to evaluate it further. So there's lots of questions around that. And there's a lot of questions around the timeline. Getting a nuclear power plant started by the end of this year, that's a tight schedule. The NRC has not been known to move fast. Nuclear in general doesn't move fast. And so it's a very demanding timeline. The second aspect is there's discussion of having these small modular reactors installed by 2030. Those are in the 10 to 14 year time bracket. How does that work? There are lots of open questions. So the purpose of all this, I hope, has been useful in just contextualizing everything that you're reading these days. I would love to get into individual questions about what you are seeing, what you would like to know more about, because there's a lot of unknowns in this.
Okay, so Max, when you think of where we were in nuclear energy now, what keeps you up at night? And it's not that newborn.
Yeah, I was going to say, it's a 4-month-old. What keeps me up when it comes to nuclear? I think that nuclear itself isn't what keeps me up at night when I think about the energy system. It's about how we're able to bring together all the different aspects of the energy system. We have many of these technologies. We have many of these options available to us in the energy system. We just need to use them and implement them and connect them. We need to connect the technology, the policy, the social systems around these. We can't just have one or two of those branches. It needs to be everything.
Okay.
And what keeps me up at night is thinking about how we're not doing that. And so our energy system, which could be so robust and so flexible and dynamic to be able to handle the challenges, gets really bogged down because we argue over many specific details rather than trying to actually solve the problems.
At a systems level.
As a systems level. Yeah.
So here's another one. I'm just going to read these as they're written. What do you think of storing waste on a moving dune? How much water does an SMR produce? And I think there was some notes in the margin about climate change and just the unpredictability of storms, that sort of thing. So I think it's a risk question, I think.
Yeah. So storing the waste on a moving dune doesn't necessarily seem like the best idea. I am not an official representative of anybody right now. So I want to say that first and foremost. Storing something on a moving dune seems like a challenge for making sure that it is constantly stable, constantly protected. I think that the bigger issue is not having a permanent option right now. None of these sites were designed to be permanent waste repositories. So this is a specific issue, yes, but it is indicative of the larger, more pressing issue of us not pulling together a permanent strategy. And then how much waste does an SMR produce? It depends on the design. So there are some small modular reactors, which are talked about in terms of those fast breeders, we'll say, the ones that consume waste. Those will produce less. Some of these might produce more because they're smaller, and so they're not able to burn up fuel as easily. There are different factors for different designs. So I won't say one direction or the other how much waste it produces, because that's a very open question that's design specific. The one thing I would say is that for some of the designs, particularly of microreactors, there are some which are designed to be fueled in factory and then run for 60 years and then go back. And so it wouldn't necessarily be like you're having waste go out of a nuclear power plant and stored on site. You might have just like this nuclear battery that runs for 60 years on the site. Those are primarily for more remote locations. So there are different methods that different companies, I think there are more than 80 designs, and about 80 different ways people are talking about waste.
So when you referenced industrial heat, are these like foundry operations, melting metal, melting aluminum, that sort of thing, where they need that real high heat?
Yeah, so we were looking at high heat industry in different brackets. So there are some that go up to about 300 degrees Celsius. Some things like drying corn, they just need 150 degrees. Ammonia production, fertilizer production, chemicals manufacturing. These things need temperatures higher than we can easily get with other renewable options, we'll say. Hydrogen people talk a lot about, but I'm not a hydrogen researcher, so I don't talk about it as much. And so currently these are mostly served by natural gas. One of the interesting things about these high heat processes is that even though SMRs are a high cost option, and I'll say this about nuclear in general, SMRs can be a high cost option. That doesn't mean that they're the lowest cost option for their specific niche. There are many different constraints that mean that this high cost could be the cheapest systemic level. And so that's something that we just have to factor in, and why the high heat processes, like chemicals manufacturing or refining, was a really key location to get these started to reduce the cost for others.
So there's two questions in here, and it goes something like this. Without SMRs, why is each reactor unique? What prevents standardization? And I think both questions are saying, you've said how the SMRs are going to be fairly standardized, but the other ones are not. So they're digging at that. Why?
Yeah, that's a great question, and it comes down to size. It comes down to what can be transported. Oh gosh, okay. So these white structures in this picture are the containment structure. That's where the actual process is happening. And so to build that, you have to build it on site. You can't transport out a whole building that size because it's just not feasible to get that from one location to the other. Which means that you need to study the entire soil system, which is great. You need to study these. Seismically, it's very important to understand your surroundings for a nuclear power plant. But when this containment building needs to be specifically designed and built on site for a specific circumstance, rather than a smaller contained vessel which is able to be more flexibly sited within still a unique building, it adds to the cost significantly. This power plant was actually tried to be modular. So the AP1000 is the name of the reactor that was sold as the modular nuclear power plant. They found design flaws partway through the design and had to have it relicensed. There were delays in getting the pieces of this to the site, rather than what small modular reactors could do is just travel to a site. So every one of these buildings had to be unique, which meant that the entire system was unique.
So here's another question. This is interesting. Someone wants you to comment on Bill Gates' sodium project. Can you do that?
I can do that. All right. Bill Gates' sodium project is, if I'm not mistaken, and I apologize if I'm conflating two designs, the Natrium reactor from TerraPower. So it's actually that sodium-cooled reactor design that is furthest along in the advanced reactor deployment. And I forget when it's supposed to be built. Ooh, that was too close. I forget when it's supposed to be built, but it is fairly far along. Sodium is a better heat transfer than water, than gas. And it has a built-in storage system in terms of being able to be more flexible. If you've got, let's think about like solar and storage. You're able to deploy that electricity at a later time when it's actually needed. Same thing for a nuclear power plant like this. You want to operate it constantly. Remember, over 92%. It's not that great economics if you shut it down. But what they're doing is they're saying we have storage on site. So we operate the core at the same level the entire time. But then sometimes when the electricity demand is lower, we reduce how much we send to the grid and we store more. And then other times when the electricity price is higher and there's more demand, we release some of that storage, but our core stays relatively flat.
So important safety lessons were learned from these disasters, the three that you talked about. How can we justify reopening Palisades without bringing the plant up to current safety standards? Which I wouldn't think we would do that. Using what we have, and then it says using what we have learned. So again, this feels a little Palisades specific, and I know you probably don't have that kind of knowledge, but I think more broadly about it, three big disasters, a lot of lessons learned. How are these being incorporated back into, new starts or restarts, like what we're experiencing here in this area?
Yeah, that's a great question. And you're right, I couldn't say exactly the internal workings of the Palisade plant and how it's going to fit into this exact question. What I would say is that one of the reasons the licensing is so strict from the outside perspective, I'm not in either the power plant business or the commission, is that we're trying to make sure things don't go wrong. And so if the regulatory process is concerned that there is going to be an issue, for example, the re-sleeving. So these steam tubes that transfer heat from the inside to the outside of the containment vessel or containment structure. If there's a re-sleeving of those, they need to guarantee that that material can handle that condition. It's a high temperature, it's a radioactive environment, so materials get really funky. It's a very strange environment. Like metals don't behave correctly sometimes over time. And so they need to prove that that metal or that material is going to behave correctly. If it isn't proven, or if there are even questions about it, it gets really slow for the process because they need to guarantee that. They're not going to say, well, we haven't had an accident with this material before in other places, so let's just run with it. There's more on the line here. And so these accidents have only increased scrutiny, which is in some ways a good thing, that we are scrutinizing these processes.